interface at one state. Okay, yes, thank you. And it's about making decisions. So so these are the realizations here. Realizations of X. They serve as an input to our algorithm or to our computer. And in decision making, so what is decision making about? Decision making means we also have an output. And this output is a random variable y. For simplicity reasons, we model this y being a real random variable in R. Okay, this is for simplicity reasons. So the example that we had was we had an image. Right, an image that we transformed into a p-dimensional vector with grayscales or whatsoever, and the output was whether the image shows an apple or a pear, whenever it was an apple, it was a +1, when it was a pear, it was a -1, and so we had to decide upon this input vector whether we decide for -1 or for 1, right? If you remember that, and in order to do that, we had the decision function. And the decision function was exactly this function f that took a p-dimensional vector and assigns it to an r-dimensional vector. And what it should do, this decision function, is that to a concrete realization of x, it should predict the best realization of an output y, or the best corresponding realization of an output y. So that was the idea. So f from Rp to R, and for concrete realization x of x, f of x should predict the most plausible realization y of our output y. Okay, and so that's the decision function, and we had to formalize what this most plausible here means, and how can we measure that. And to that end, we say, well, we need a kind of function that measures this deviation, and this function was called the loss function. And the loss function here is actually a function that has two real inputs and assigns to it this deviation, this r plus 0, and it measures deviation of f of x and y. Okay, and yeah, so I mean, we had last time we talked about the squared loss function, for example. There are others, and the smaller this function is, the better it is. And the idea was that so if I plug in here a new, so if I look at the distribution here of this y and f of x, if I plug that in, then this is a real random variable. because I have two random variables as input, and it's a real random variable. We had two approaches to find what the best function f is. Right? Remember that we are looking for what the best function is. And one thing is that the best decision function was one that minimizes the expectation value of this random variable. Right? There is one break too much. So, no, it's not. Okay. This is called the expected loss. In practice, we don't know anything about the distribution except a few training samples, or it's been just the samples. So this expected loss is approximated here by the average. So this is 1 over n, and you sum up over I, and here you have your loss function, and you have your yi, f of xi, and the xi and yi are samples from the joint distribution, and this is also known as training data. For our function and f here, because we don't want to search, or we cannot search for an infinite, if the search space for our function is too big, it doesn't make any sense. So in practice, we have f out of a predefined chosen function class. So f is chosen out of a predefined function class, right? For example, affine functions, or linear functions, or quadratic functions, and so on and so forth. So the larger the class is, the better we can minimize the expectation error. This is somehow clear, but also the more complex it will be to find this function. So it's always a trade-off. That was one thing. And the other thing was that we say, well, right, I mean, if we look at this example here, we see that all training data that we have are somehow taken into account, and we take information about samples of the whole distribution of x and y. And sometimes it may not be so, it may not be such a good idea. If you remember the example that we've discussed last time, where we decided upon a certain xi and wanted to assign a 1 and a 2, it was also meaningful to just look at the nearest neighbors and somehow ignore what xi's are doing if they are far away from this x. And that led us to this other, to another approach of looking at that, namely looking at just the best value of the decision functions, right? So the best value of the decision function, right? So, I mean, here you get an explicit form of your decision function f. For example, an affine function, you compute the parameters of your affine function, you can store this function here in your computer. In the other approach here, you will not get a parametric form of your function, you will just get an additional value given some certain x. And this is this local way of looking at the things. So the best value of the decision function given a realization of x. And that means that we want to minimize, right? So this is the best value, the c hat value, and it should minimize here the expectation value of the loss function y given here, but we only look here at the conditional distribution of y given the realization of x. So this is the thing, and with that we will not get a closed form solution for the function f, but just the value c hat. Okay, and this here is typically approximated by the this is the average for y in a neighborhood of x. Right, formally write that here. So we sum up the values for yi, and I is here in an index set ix, and then here we average, and this index set ix is just given by all I where xi are close to x. Right? And of course here also close, what does close mean, needs to be defined in a concrete example. So you take, for example, an L2 norm or an L1 norm or whatsoever. But that was somehow the summary of what we did last time. And we have perhaps some room for questions or answering some questions. Is it also on Mondays? I see.
So there's only one question, which is what is the L? So I think he's referring to the loss function.
No, he means what is I?
What is
okay?
What is the I?
Yeah, I think towards the index.
The I is an index set, right? So it's you have your training data. You have your training data here, x I y I, and the I is just, it counts just your training data. Okay, so well, it's the index of your training data. If you have 10 images, if you have 10 labeled images, then I goes from 1 to 10, and the first set is image 1 with nose 1. Okay, and image 2 with nose 2. This is the index. This is small I. Okay, good.
So
okay,
there's no other question, I think, for now.
Okay, good. Okay, so things will become probably more concrete during these lectures. So this is the broad overview of the way we can look at these methods here. I will also say something about this part, right? The part of how to model somehow the real world, in particular of how to model text documents, because they do not naturally occur in numbers, and perhaps at the end of this lecture. Let's see how fast we are. Okay, good. And then we discussed, you remember that we discussed a few examples, and I would like to go back to the slides, and I have to do that. Stopping here, and then share my screen.
So, students, if you have any question, you can please ask in the chat.
But also, I mean, if I should repeat something or so, right? I mean, as long as the questions are not like 10 questions per minute, we will have enough time to really go into all of these questions. And be sure, if you have a question, the probability that 1 out of your 103 colleagues also has this question is quite high. Okay, let's see. So, yes, so that was the slide I showed you last time. Right, so you remember, I mean, this was the thing. So here I is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 60, right? I goes from 1 to 60 because we have 60 training samples. We have you know, X. I can make it a little bit concrete here, perhaps. X here is a vector. I think it's in R64. Is that correct? It should be 8 by 8 pixel or higher. 16 by 16. Do you know it by heart, Umer?
What? The size you mean?
The size.
I think it's 224 by
Yes,
224 into 3.
The size.
I mean, it could be 64 by 64 into 3, and also 224 into 224 into 3.
Okay, anyway, so this here is in our, okay, I don't want to do that. RP, right? It's the number, and P here is the number of pixels of one image. Okay, let's make it like that. A realization, pixels of image, and the value. So the value here, xi, is the gray value or grayscale of the pixel. Okay. This is the xi, and yi, and y is 1, or y is -1 here if image shows 2, and it's 1 if the image shows 3. Right? So these are the random variables. This is how we model it. And for local decisions, we see, so this is the new data x coming in. Here, this is our x. And what we do is, well, I mean, we set k equals to 7. I mean, we can also choose k equals to 10 or 5. It depends. I mean, the larger we choose k, the more we deviate from the actual, what the theory tells us with the local decision making. But K7 is chosen here in that example, and so we look at what are the 7 nearest neighbors to this image, and nearest was measured with the Euclidean distance, and then we see, okay, so.
But Martin, I mean,
yeah,
here could be a question. You are saying that you are measuring the nearest neighbors in a very high dimensional space. I mean, if it's 224 by 224 into 3, So then it's a very high dimensional space. So is it meaningful to measure the distance?
No, not at all. Yeah, it's not at all meaningful to make the distance here. Yeah. But this is what I want to talk. What I want to talk about in the remaining 45 minutes or so, because I want to talk about the curse of dimensionality and say that this is not very meaningful. It's just to show you, to give you a glance of how these methods work, and then, right, if this method would work, we could stop the lecture here and go home, right? I mean, this is then nothing, you know, I mean, then we would nothing would be left to do. But since it is not a very good method, we have to circumvent these issues. So it's a good question. Yeah. Okay, but just let me finish that so that you understood at least what we did here, regardless whether it's very good or not. But this is what we have learned so far. So this is the 1, 2, 3, 4, 5, 6, 7 nearest neighbors, and the nearest neighbors vote for y being -1/7 on average. So that's the expected value that we estimated, and so we would vote for. So we would vote for Biden. Vote for -1. Yeah. Yes. Okay. So just for you to understand this example. Now, next, and now we come to the next section here in this lecture. That is, I mean, we have seen that in these examples that we discussed and in the way we approached the problem of decision making, the prediction, regardless of whether we go to this global view on the things or on local decision, it either needs an estimation of the probability distributions or nearest neighbors, and that's really the problem, that in high dimensions, and we really talk about high dimensions, I say about things something later, is that probability estimations become less accurate, and that there are no such thing than nearest neighbors in high dimensions. This is the phenomenon here that is called curse of dimensionality. I come to that later. Just, I mean, summarize what we have learned so far is that we have looked at 2 classes of models for decision making. This global one that incorporates all points in the data set, and we reduced our complexity of the problem by learning the parameterized decision function. And there are local methods, and these local methods incorporate only data points in a region of interest. Local methods are more flexible because we do not have to restrict to a certain function class. That's the advantage here, but it also causes challenges in high dimensions. And now let's look at these challenges in this curse of dimensionality problem. Yeah. So if we look at this problem of modeling our environment and if to design an input variable, right? I mean, we are at the point where we say, okay, if our input variable is only 1 or 2 dimensional, if p is 1 or 2, we don't need machine learning. Okay, then the problem is somehow solved, because then these problems do not occur. So it's really something that is based on these high dimensional things. And for example, if we look at business processes that have often time series or so, and we want to model that, you come to a p that is quite high, right? Probably like 100 dimensional. If you look at these visual objects, you immediately come into p in the range of 1 million. This is, or if you look at text documents, you will also see that the p is rather large. And the less we know from our environment or from the data that we gather, the higher we choose the dimension, somehow in order not to lose any important information. And this p in this high dimension causes us problems, and these problems are known as the curse of dimensionality. And I would like to start with, I mean, there are three aspects, and the first aspect is that the distribution estimation is very tricky if the dimension of the distribution is very high. So estimation of the probability distribution from samples is difficult in that case. And I would like to give you a kind of feeling what that means. Okay. So if you look at, for example, I mean, you all know the 1D Gaussian probability distribution function. This is this guy here, right? And if you take 4 random samples from this distribution, they could, for example, look like this. So that could be 4 random samples categorized in bins from this probability density function. Okay. Now, if you only have these samples, right? If someone of you gives you these samples and say, now, come on, guy, look at the 4 random samples that I gave you. Go ahead and estimate the probability density function of the underlying distribution. And you would need to go backwards and estimate that. There are ways of doing that. I don't want to go into the details, but you can. There are methods that input is for random samples and the output is an estimated density function. And you can imagine that if you want to somehow reconstruct the underlying density function, given these 4 samples, it's probably not very accurate. Okay. And you can measure this accuracy up to a certain threshold. And you can do the same thing for a 2-dimensional Gaussian distribution. So you have a 2D Gaussian distribution. And if you want to be as good in reconstructing the underlying probability density function for the 2D, you already need 19 random samples, right, to get it with a certain quality. Right? Reconstruct with certain quality, and here reconstruct with the same measure of quality. I don't give you the explicit measure because it would somehow be beyond the scope of this course. I just want to give you somehow the idea of how that could be done. And you can imagine that the quality is not very high if you look at the 1-dimensional example that you can probably grasp better. You can keep this quality here constant, and you go from how many samples do I need in the underlying probability density function with this certain quality. You come to this table. This table is so this is the dimension here, P, and this is the number of samples you need to reconstruct it with a given quality. And for P equals 1, we had these 4 samples. For P equals 2, we have 19 samples. And already, if you grow here, your dimension, you in order to estimate or in order to find out in a certain quality what a 10-dimensional Gaussian distribution would be, you nearly need 1 million samples already. Okay, and the number of required samples that you need is approximated by this function here, and for n equals 140, so for 140-dimensional Gaussian distribution, you would need 7 times 10 to the 83 samples in order to get a rough estimate of what the true density function behind is. Okay, so that's really a lot, and it's also really, I mean, it also tells us that you need some theory to overcome this problem. I mean, you will not solve it by saying, well, if I just have enough training data, then everything is fine, and then I can guess every underlying probability function with a good quality. Because I mean, if you I don't know whether you knew that. So just for comparison, some physicists have counted the atoms in the universe, and they counted a long time, and they ended up at 10 to the 82. So there are about n to the 82 atoms in the universe. And for estimation of this 140-dimensional Gaussian distribution, you would already need 10 times more than there are atoms in the universe. Yeah, so that's a fun fact here. So that is not relevant for the exam. And this is also not relevant for the exam, but if you're interested, you can have a look at these two really nice papers, and there are some more details, and also this measure of quality of how we can reconstruct that are given there. Okay, so in order to estimate a distribution that is high dimensional with training samples, just forget it, right? There is no way. Another interesting thing of what's happening in high dimension is the following. If you look at the Gaussian normal distribution here, and you start with drawing a sample like that, you would probably lie here, for example. Okay, so that could be one realization at that point. You do it another time and say, well, okay, so this is here probably the next distribution, next sample, and you see, if you look at this distribution, that the samples that you draw here, they are they are most of the time near zero. Okay, so that is the weight of this probability distribution. Okay, not so much of a surprise, because this is where you have the highest density. What happens in higher dimension is now, so let's call it, I mean, this is x1, this is x2, this is x3, right? And you draw your samples, but you know, all of a sudden here you have this x4 perhaps, and then there are many samples here, but one day, if you just draw your realizations long enough, you will have one outlier here, right, in this point. This is probably here x, I don't know, 17 or so, and it will lie outside. If it's not the 17th, it will be the 20th, and if it's not the 20th, it will be the 30th. That is somehow outside. So if you go to higher dimensions, and if you say, well, this the x is somehow distributed, xi is distributed here 0, 1, and you have your x in Rp, right, and P is large, then your realization of x, that looks like you have your x1 here and your x2 here and your x3 here, but at one time there comes this x17, and this x17 makes your whole realization of x somehow an outlier, and this is somehow responsible, right? If this is you know, far away from 0, and that means that the whole norm of x is large, and that the whole x is away from 0, right? I mean, this is a hand-waving argument, but you somehow can grasp it, that if you have p independent realizations of your components, then with very, very high probability, one component will be so large that it deviates completely from the mean of the whole vector, and that it lies outside. We can formalize that, and that's what we've done here. So in high dimensions, samples tend to lie in the distribution's tail. So this is the counterintuitive. So this is somehow counterintuitive if you look at the one-dimensional example, but high dimensional this is like that. And as an example, so what I've written here is somehow a formalization of what I've just drawn. We have this x in Rp is a random vector. All components of x here are independently identically distributed, and they should be distributed such that the probability here that the norm or the square of this xi is smaller than beta is not 1, but is smaller than 1. It's fixed, but it's smaller than 1. This is the case for any distribution that has a support from -infinity to +infinity, like for example the Gauss distribution. And if this is the case, then we can easily show that the probability that the norm of the squared norm of your vector of the realization x exceeds any boundary beta goes to 1, goes to infinity. Yeah, and the proof is rather simple. So we have this probability. So the squared norm here of this vector xi exceeds this beta. That happens, of course, if already one of this xi squared exceeds the beta for at least one I. Now going to the counter event, 1 minus probability of xi squared is smaller than beta for all I. And here we go for the IID distribution. So that means that this probability is the same for all of the I, and we can bring that together. And this is the probability of xi squared is smaller than beta to the power of p. So yeah, and this of course goes to 1. This goes to 1 as p goes to infinity, right? Because this colleague here is smaller than beta. Is smaller than 1. It's fixed and smaller than 1, so it goes to 1. Right? I mean, this is nothing else than what I have explained in the previous slide. Oh, sorry. What I have explained in the previous slide. Yeah. Okay. Good. That is one thing.
Okay, so yeah, I think it's a very good time for a break.
Yes, I also think so. Perfect.
So we have a question. Maybe we can discuss that after break, right?
Yeah.
Let's take a break. Okay.
So yeah, let's have a 5 minutes break until 10:30, and then we do some to gather some information with it. Yes, thank you. Right, and so what changes is that in practice the xi are correlated, and that allows us to find some intrinsic structure in the data, and with this intrinsic structure that you have, then that allows you to get the information extracted, actually.
We will also have an exercise in the tutorial where we discuss this phenomena with some examples.
Yes.
So Patrick asked a question: why do we take probability of xi squared, y squared? Why are we taking the square root of the L2 norm?
Also, well, I is smaller than some gamma, right? It's the same thing.
But with the square, this derivation becomes like easier to solve because we get rid of this under root in the second step.
Yeah. Well, but it's not even easier. It's just the same thing. Smaller than gamma squared, and then you have beta is gamma squared, and it's actually the same proof. Okay. Good. Then let's continue. I mean, there were the two things, right? There was this estimation of the distribution is not so easy. Then also the samples lie to tend at the tail of a distribution, which is also somehow counterintuitive. And the other thing is that the samples, and this is what it means, that there are no nearest neighbors. Samples in high dimensions tend to be equidistant, and this is I mean, you can find that in one dimension we have sample. Let's look at this here. So there are some samples, and the distance here, the pairwise distance, is here rather different. So if I have, so the distance from this point to that point is of course larger than from two intermediate points. And here they do not tend to be equidistant. But the higher it comes in the dimension, the higher it comes, the more you see that these pairwise distances that occur here tend to be the same, right? And this is formalized. So I mean, there's an example. I don't know whether you're doing that in the tutorials or not. Are you working on that or not? We did that once. So we have an example. We have like 158 phase images, and we take them purely as they are in the high dimensional space with the gray values, and we compute the pairwise distance, and then we plot the distribution of the pairwise distance.
Yeah, we have this.
Yes, so that's good if you talk about that, and we see that most, right? I mean, most of the pairwise distances are somehow concentrated around 2 to the times. So it's 20,000, right? Whatever that means, but it's somehow concentrated to that point. So there is no information, because most of the time the distances, the pairwise distances, tend to be the same. So that should somehow reflect this phenomenon with real data. And you also see, and that's interesting. That's also an interesting plot, because if you have cats instead of faces, and you plot the pairwise distance of cats versus faces, it even carries less information than faces versus faces. So that's somehow the thing, right? I mean, so the pairwise distance of cats versus faces is concentrated even more around 1 point than it is of faces versus faces. So that should somehow reflect this phenomenon that if you look at these pairwise distances, that does not carry too much of an information. It can also be formalized. So this is the theorem, if you want. So if you look at a p-dimensional, random variable, and you take another, so it's a p-dimensional random variable, and you take n realizations of the p-dimensional random variables, right? I mean, you have here this here is x1 is this, and this here is xn, and they are all p-dimensional. Okay, so this is how you have to read that. And you have some q, which is also in RP. So these are all high dimensional realizations, and they are drawn independently according to a given distribution, right? To a given distribution in RP. Now, if we define distances of this q to the realizations of xi, and we look at the minimum. So we have a realization of q, and we compare it to the distance to one of the xi, and we take the minimum value of it, and we take the maximum value of it. Then, under certain assumptions on the distribution, we see that the distance, so we see that the probability that the maximal distance and the minimum, the difference of the maximum and the minimum distance, that this is smaller than some epsilon, is going to 1, which means that there is actually no, so that this can, if p grows, that would be arbitrarily small. Okay, and then it sees that d max tends to be d min. This is how you can read that under certain assumptions on the distributions. And also here, this is the nice paper that goes into much more in the details here. But when is nearest neighbor meaningful? That's the thing. Okay. So having that said, it means that, well, we want to get rid of this high dimensions. We want to reduce it, and we want to make it smaller, and we want to make it digestible, and we want to extract information out of this high dimensional random variables p, and we have seen that this is actually not so easy unless there are some correlations in this xi that we can exploit. Okay, and these.
Okay, so Martin, can you please go back to previous slide? So there are some questions regarding
this one.
No, the next one.
This one.
So what is q here, and what is xi?
Well, q and xi, as I said, they are q and xi are both samples from the same distribution. They are samples of a high dimension of a p-dimensional distribution. The q is just called q because you can also name it x nu or so. It has just another name because this is the reference point, if you want, the reference sample to which you measure the smallest distance to all other n data samples that you have somehow sampled beforehand.
Okay,
does that make sense?
Yeah, I mean, that makes sense, but maybe to put in other words that we select randomly a point q in a space, RP space, and we want to measure the distances of all other, let's say, n points from with that point. So q is the reference point, and we want to measure like x1, x2, x3, x up to xn, and we want to measure the distance between them.
Yes.
Okay.
And you measure the distance between all of them, and then you take the minimum distance that you achieve. And here you take the maximum distance that you have. Like q is the reference point, and all the other endpoints are. They give you n different distances. Is that okay? Good. The max and the min become nearly equal in high dimension data. Why is the limit p infinity gleich 1 and not 0? Slide 40. Slide 40. Probably this slide here. No. Slide 40. Slide 42. Okay.
So I think he's talking about the last equation, that when p approaches to infinity, then y is 1.
Yeah. So you if p increases, then almost surely, right? You are beyond any threshold that is foreseen. So I mean, this equation needs to be read in the following way, right? Umer gives me an epsilon, right? Umer says, haha, epsilon is 0.01, and try to make that the maximum distance and the minimum distance do not deviate. So the relative maximum and the relative distance, because you're normalizing here, are not smaller than 0.1 or 0.01. And this is what Umer gives me. He gives me this epsilon. I say, haha, okay. Then if you let me choose my p, right, regardless of the epsilon that you give me, almost with probability 1, almost sure, I can make this quotient smaller than the epsilon that you give me. Okay? For all epsilon greater than 0. So this is the game, right? Umer gives me, Umer or Rayyan, it doesn't matter. They give me an epsilon. It can be rather small, but it has to be positive. And then I say, okay, so to that I give you the p, and I raise the p, and there will be 1 p, so that almost sure I'm smaller than your epsilon. I cannot explain it better, I guess. I can only repeat it or say it louder.
Yes. Does that answer the question? Maybe yes or no?
Okay, cool, good. Then let's continue and see. So that's somehow the idea behind. Okay, we need to look at our data.
I think let's move back to 42 slide. Just 1 second. I think maybe there was a little bit of confusion because people are thinking that y is equal to 1. Is it a probability or is it a distance? So this is because the probability sign is probably missing from the Yes, I think that caused the confusion.
Yes, of course. I'm sorry. I mean, yes, then it doesn't make any sense. Yeah. The probability is missing. I haven't even seen that. Of course, we're talking about this probability thing. I'm sorry. Yeah, but we need to change that. Okay, thanks. I hope that, okay, now I hope it's clearer. Yeah, good. Okay, so that means that all we can do with this machine learning stuff is exploit the intrinsic structure of the data, and reduce somehow our dimensionalities in a meaningful way, so this suitable mapping that reduces our dimension from RP to RK is what we are looking for. And also in this course, we talk about RP as a raw data space and RK a reduced data space, or also sometimes called a feature space. And if we can meaningfully reduce the dimension without destroying information, then this is actually what machine learning is about. Okay. So there is one example here that where you say, so we maintain information or intrinsic data of the structure. We have a high dimensional space P, 784, and we have different digits, and we want to map it to k equals 2 without losing information somehow. And this information is, I mean, this is the t-SNE algorithm, how you can visualize data, and it is a method that only uses it's not a supervised method, so it's a method that only uses the intrinsic probability distribution of our x. And so this is here the input x, and it reduces the dimension to k equal 2. And if you look at it, you see that it can do it in a reasonable way, because the 4, this is probably the 4 is somehow contained in a nearby region. The 0 is somehow contained in a nearby region, and so this algorithm does a good job. Okay, so but this is the aim: reduce the dimension while maintaining the information. And actually, you can do that you can reduce it in 2 ways. One is called supervised learning. where we have labeled training data, we have this input and output, right? Input X, output Y, and we have information that has to be maintained is given by the labels, output Y, also called labels. And we map data with the same labels to similar feature values and with different labels to different feature values. So there we can use it, this labeling. If we do not have any labels, and if we want to reduce information just by looking at our input variable X, where we have no labels required or available. Sometimes you wish you had labels, but you don't. Then the information to be maintained is in the intrinsic data structure. And this intrinsic data structure is exactly the correlation that somehow is the difference between this white noise on the television and a structured image. Okay. And if you, for example, if you want to plot white noise, I try it. Okay. If you want to plot the distribution here of X, and you have here X1 and X2, you have here two variables, and they are somehow uncorrelated, then you would probably have noise that lies in that way. If you have some intrinsic structure in the data, sorry, X2 and X1, it could probably look like, I don't know, this. Okay, and then you have a kind of intrinsic structure here that you don't have on the left picture. And actually, what you can also look at, I mean, you can also look at this unsupervised learning in a way of that you want to reduce the data volume while maintaining an intrinsic data structure. So let's see how that view on the things will help us in designing algorithms later on. Yeah. Right. So left-hand side here is no structure, and here we have some structure. And I mean, very often you have this a linear correlation between the data. Well, this will be the first thing that we start with. Okay. Well, okay, so there are also hybrid approaches exist. They are named semi-supervised learning, but we will not discuss that here in that lecture.
So we have a question, I think, which is quite related. The previous slide. So Lenovo is asking that is the intrinsic feature specific to the kind of application we are working on, or it's generic? Can you tell an example about these features?
Yeah. Yes, we already had last time we had an example that was not formalized on the paper, but you remember perhaps if I said, well, can you recognize the image? We had this story about can you find me, right? I mean, I showed an image last time and I said, can you find me? And you said, yes, you can. And the idea was what you did somehow, what your brain did is you reduced the amount of information that you visually got through the image. You reduced that, you stored it, and then when you saw me, you recognized, okay, so the features that I had, they map somehow to the other image that I see. Right? So this is so somehow in your brain you stored intrinsic features, and they were specific to the kind of recognizing people, because your brain is somehow trained in recognizing people because you're human, and so you're used to it. Okay, it would probably be a harder job if you would look at, I don't know, QR codes. recognizing QR codes. Of course, there's also some intrinsic structure in it, but you would not be able to distinguish two QR codes because your brain has not learned these features. That was on a very high and abstract level.
Yeah. So I would just like to add something. For example, here Martin, let's say, said that information is to be maintained in the intrinsic data structure and then pairwise distances and clusters. So for example, we would assume that, like in case of MNIST dataset, so for example, if we have one, then we would need that. I mean, if we reduce the dimensions, then in this new space, let's say 10 dimension space, the ones should be closer together as compared to 1 and 8. Because 8 looks a bit different, quite different than 1. Maybe 1 and 7 are closer to each other. So it's just like this kind of features which we assume or which we hope for, and the good things, basically the good algorithms do that. So it's application specific and also general. So it's both kind. Yeah.
And we already had an example of this type of feature in the previous slides, where similar clusters were together and vice versa.
Exactly. That's that thing.
And yes, right. I mean and you're right. Both types are mainly important. If you have an unsupervised problem, for example, the feature extraction can only be defined by the intrinsic structure of the data. So take, for example, clustering. You have data and you want to reduce your dimension by saying, okay, I'm just looking at the center of clusters of my data. So that also reduces the volume of the data samples, as I said. And the clusters are there. Right? And if you look at pictures of flowers, for example, you can see, well, I mean, the cluster is there regardless of what you want to do with this information. It inherently comes from the data that you look at. And you can have other, and then the cluster would be, for example, a feature. Okay.
Let's move ahead then.
But to finalize that, if you have labeled data, then of course your algorithm can also learn features that are relevant for the decision you want to make with it, or for the categorization. Right? If you want to, if you now want to analyze flowers, for example, and you always label white flowers as white and other flowers as non-white, and you learn a classification algorithm, then of course your algorithm will learn over time that the relevant feature is probably the amount of white pixels in your data. Okay.
Yeah.
Okay. Good. So yeah, let's move on. Okay. So yes, summary for that part was that an unexpected phenomena, they occur in high dimensions. Play a little bit around, perhaps also in the tutorial with these high dimensions, and then you'll see what that means. It is difficult to estimate the underlying distribution. Samples tend to lie in the tail of the underlying distribution, and samples tend to be equidistant. Right. This is also, I mean, here also some of the noise plays an important role in what you have, because very often you have an underlying broad structure, but the structure is somehow deviated by noise, and the noise has an IID structure. So yeah. So reducing the dimension can also be seen as reducing noise. And we use dimensional reduction to circumvent these issues. Good. So yeah. Yes, I want to start with a new slide because we have another 15 minutes. New set of slides. Yes. Hold on. No.
So it would be great if someone has any question, kindly post in the chat.
So this was the thing I would like to show you now. It's about the design of this random variable, right? How to model the world that surrounds us. That working, or it's just too slow. Can you see this slide? Recall from phenomena to data. Okay, yes.
Yes.
Okay. Good. These are the typical tasks I talk about it. Now, data preparation. So assume that you look at your environment and you see this, right? And you want to model that with a high resolution. Could you share the slide with us right now? Yeah, I'll share everything I have with you later. So so the data preparation. We have images. We have sometimes speech signals, and all these signals come with very high dimensions and in very different forms. We have, for example, log files that we want to analyze or that we want to learn something about, right? Emails that we want to classify in spam or not spam, and all of these things. And to all of what we observe in all these real world phenomena that are out there, we want to build random variables that we can analyze and train our machine for. Right? It becomes more complicated. For example, if you look at data that is quite diverse, you have a text here. Right? As you see, you have a text, a description text. You have images of something, like article. I mean, of course, this is something we do at Mercatio. And not only that, you also have very informative, like strings here that are not. You have a manufacturer number and all these things. So this is somehow, hard to model and to see how you can grasp that. And how can we get to representations of this data or to these random variables? And there, the data preparation is quite important. And I will only give you some guidelines in which, if you have a practical problem, that you should check somehow these guidelines. Have I thought about this? Have I thought about that? Because individually, this is for each problem, this is an art on its own to do that. Ideal representations of the data gather only the useful information that you have. So this is somehow task dependent. What do you want to do with your data? And that are complete, so that no missing data is there. This is one thing, and that they are consistent. So if you gather data about someone, you have age is 45 or birthday is 3rd of July 1973, or you have a rating that is 1, 2, 3, and now the rating is ABC. All these things that occur in practice that occur in practice are there. Okay, consistency. Now, from this consistency, I mean, I said at the beginning, we are working with random variables, and before you have random variables, there are different types of data that people somehow distinguish, and that also have an impact on how I design a random variable then. So one are the nominal categories that describe our surrounding world. Nominal categories, because no ordering is possible. So this is how I remember it. No ordering is possible, so nominal categories. For example, gender, race, religion, persons, apple pears, classification tasks that we have. These are typical nominal categories, persons on an image. But you have ordinal categories where an ordering is possible. For example, small, medium, or large. Strongly agree, strongly disagree. These are things that typically happen in psychology or so, or in these kinds of social science
Business marketing also.
Business marketing, and we're not using that actually. So okay, good. So nominal categories, ordinal categories, and of course the quantitative data. This is numerical data that we consider as realizations of typically high-dimensional real random variables. And why are we restricting to that? Well, because you can map very easily the other kind of variables onto a random variable, and I'd like to say you how that works. So first of all, you can go from numerical to categorical data. If you go for discretization, that means equi-width, equi-log width, equi-depth ranges, and so on and so forth. So if you have, I'm drawing it just in 2 dimensions, just to tell you how trivial that is. So you have your, in this case, a 2-dimensional numerical random variable, and what you do is you somehow cut your space, I don't know, into 4, and then you have category 1, category 2, category 3, and category 4, right? For example, you can do that with equi-width distances. You can take the logarithm and so on and so forth. There is no limit to your fantasy of how you can do that, depending on the problem. But it's not so interesting for us. More interesting is going from categorical to numerical data. So how do I come from apple or peer to some random variable in some R, yeah? K, whatever. Let's take orange, apple, and pear. And because if you only have apple and pear, we already did that, and we said, well, we go to R and we go to -1 and 1. Okay, that's good. If you have a third categorical variable that you want to map and you want to distinguish between these 3 ones, the question is, how far do we go? And one way of doing that is the so-called binarization or one-hot encoding. And the one-hot encoding says that we order all possible outcomes arbitrarily from 1 to p. Here, 1, 2, 3. So in this case, p is equal to 3. And we say xi is 1 if the data value is the ith outcome and 0 else. Right? So here, orange would be mapped to the vector 1, 0, 0. Apple would be mapped to the vector 0, 1, 0. And peer would be mapped to the vector 0, 0, 1. Okay? This is the so-called one-hot encoding. And now, if you say, well, I mean, why not going into R1 and saying orange is -1, apple is 0, and pear is 1, right? Why not doing this? Because then you would have then you would introduce a kind of measure or measure that would bias your algorithm at one time, because the distance from orange to apple is smaller than the distance from orange to pear, and you would have apple somehow as apple is the average of orange and pear, which does not make any sense. Okay, so you would like to somehow map your data into a space where you have no preference. Where not one data point is preferred to another. And this is achieved by this one-hot encoding. Right? So the distance between apple and pear is the same as the distance between orange and apple, and so on and so forth. So, right, this is how you do it. And okay, so however, Is that, did it cause curse of dimensionality? Yes, yes. So the curse of dimensionality is interesting here, very interesting, because now if you have only these 3 dimensions, it's not so much of a problem, and also if you go higher, it's also not so much of a problem because you are only having p finite points in that high dimensions. So that's not so much of an issue. But what we can do now is, so the problem here is, assume that you have learned something that maps your orange, apple, and pear to one of these vectors, right? And then there is a 4th vector coming in, and you want to raise the number of categories raises over time with your problem. If the output space would also somehow grow in the same way, that would not be a good like architecture for a machine learning method. In the same way, is it actually needed to have these high dimensions if you look for, I don't know, 200 categories? And if we say, well, the only a reason why we do this one hot encoding was that we want to have pairwise distances between each outcomes and not to prefer anyone. What we can also do is we can fix a dimension p in the outcome space and say, well, we assign to each of these category a random vector in RP. So we keep the dimension 10 fixed, for example, and we assign to each categorical variable one fixed but random vector in this p-dimensional space. Right. So, for example,
yeah, I think maybe isn't this p a bit overloading here? I mean,
yes.
It could be, let's say, I mean, ideally it should be less than p, right? It should be.
Yeah. Let's just do it like that. A random vector. I think it's better because p is overloaded here. Yes, you're right. Yeah. Right. So, for example, I say, well, I would like to train a machine that is able to recognize all the students in that class. Here, so 108. Okay. So if I would do a one hot encoding, each person to you would have, I would have to assign a 108 dimensional vector to all of us. Umer starting with 1, 0, 0, 0, 0, 0, 0, then Faish L RG, or what I read here, would get the 0, 1, 0, 0, 0, and so on and so forth. And if I say, well, but 108 dimensions is actually too high and it's not necessary, because if I take the curse of dimensionality, I see that even in R17, if I assign to all of you a random vector, then I would not have this this problem of different distances, or at least it would be neglectable here. And so I would assign to each of us a random vector in R17 instead of this one hot encoding. Okay, so so here for example, the apple, I would assign orange to, I don't know, some random stuff, 0.1, 0.12, and 0. I don't know, random, right? Random. And also apple would be assigned to 0.5, -1, 0.1, and so on and so forth. But they all have to lie in the same dimensions. Okay, so this is also something that you do in practice. If you have categorical variables, you assign them, before you start your algorithm, you assign each categorical variable a random vector in an appropriate dimension. Okay. And yes, and it's mainly due to computational reasons, but also to keep it, not only to computational reasons, also to keep your output layer that you have at one point fixed, right? So everything that you trained over time that should identify 109 persons has as an output layer, I don't know, 17 or so. And if the number of, and you don't want this output layer to be dependent of the number of participants that you have in your class. But that will then become later. Okay.
Then there's the next question. Should I read it, or are you reading?
Yes, read it. Read it for everyone.
So when we use one hot encoding and we want to make predictions, we use argmax. If we use instead a fixed size vector, how do we differentiate using error estimate?
Yes, so that's a good question. I mean, if we have higher dimensional output, we need another, our loss function has to measure the distance between not only in R, but also but in RP. Right? This will be then reflected in the loss function at a later point. Okay. Good. Okay, good. So the time is over. We can, but that's perfectly fine, because then we can hook in next time and see how we can go from or how we can model texts. That would be good. And then we do this from text to numerical data and see the bag of words approach that helps us to quickly analyze the text documents, one glance, and yeah, and then that's it. So are there any final questions here so far?
So there are like two basic questions regarding uploading the Moodle slides.
Yes.
And the second is regarding your beautiful artwork slides.
I know. Yes, I'm still thinking about whether I should sell them for a lot of money or whether I just upload them on Moodle. I probably will do the second one. So I will upload it if I get it saved, right? If I get it saved here on my iPad, I try to upload it. Otherwise, but we still record, right?
Yeah, we are recording. So now I'm going to end the recording and let's hear the funny funny sound. Okay.
Okay.